I have made an egregious mistake. So last time we talked about binomial coefficients, and today we're going to do like two practice problems with them, just to show we can do some fun problems. They're actually useful to know. Um, but we ended last video talking about Pascal's identity, which is it's a neat identity with a pretty cool combinatorial proof. At least I thought it was cool. Um, but I made a mistake. And when I was writing out the proof and I got to the sentence with the mistake, I didn't make it obvious out loud, but I was thinking in my head, that makes no sense. Um, but I just kept going with it. And so I'm here to correct that. So the issue, here's the mistake I made. And it starts with our equality up top. We multiplied. That doesn't make any sense. We should be adding. We should be doing this, right? And let's think about our proof again, right? We're saying that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. And that's because we labeled this like one special element. Remember, we named an element, we said it was special, and we're like, all right, well, all k subsets of an n size set will either include or exclude that element. And so n minus 1 choose k minus 1 were all the subsets that include it, and n minus 1 choose k were all the subsets that exclude it. For some reason, I wrote down that we had to multiply them, but that just doesn't make sense. We should be adding the quantities n minus 1 choose k and n minus 1 choose k minus 1, because that's what makes sense. You take all subsets that exclude the special element, add all subsets that include the special element, and then you get all subsets. Again, I don't know why I said to multiply. Didn't make any sense, but I needed to correct that error because I it came to me, I realized my mistake, and I was like, that's not good. We're not out here spreading misinformation. So, the rest of the proof holds. You just need to add, not multiply. But like I said, now we're going to just get straight into it. We're going to talk about we're going to just do a couple quick problems with binomial coefficients, show how we can apply this counting object that we learned, right? So, I have a little drawing for us to look at. I have this grid, a 5x5 grid. If you know some graph theory, this could actually be a graph. And I want to know how many paths from start to finish. And notice how start is yellow and finish is pink to indicate that the yellow dot is the start and the pink is the finish. So I want to know how many ways can we get from the start to finish, right? Because this is a little brain teaser, right? Maybe if it was a smaller grid, like a 3x3 or a 4x4, maybe this is something, I don't know, a little brain teaser you would get in like elementary, middle school, I don't know, maybe high school, who knows? It's just for fun. Looks like I didn't finish drawing the grid. And if it was a smaller grid, like I said, like a 3x3, you might just go through all possible cases and be like, "Oh, look, teacher, I'm the fastest, which means I'm the smartest," which is not the case. But then once these grids get bigger and bigger, 5x5, and then I don't know, maybe 24x24, it's pretty big. You're not gonna be counting all cases, right? So how can we count how many paths there are start to finish, right? Let's think about this logically for a second, right? Let's take a path, right? Okay, I'm gonna go to the right, and I'm gonna go right again, and then I'll go up. Maybe I'll go right again, then I'll go right again, and then my only option is to go up, 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 boom, I got to the end. Okay, so that's all nice. But now let me take a different path, right? Let's use a different color. Let's go green, right? So now I'm gonna go up, and I'm gonna go right, and then I'm gonna go up, up, up. Oh, I can't go up anymore, so now I'm just gonna go right and right. Oh, and I should have specified this. How many paths from start to finish? Let me do this. By only going right or up, right? Otherwise, if we were backtracking, that doesn't make sense. We want to get there fast, right? So how many paths from start to finish by only going right or up? Those are the only moves we can make, and those are the only moves I was making, right? Now, again, we can't just count every single possibility. That's just inefficient, right? We don't like inefficient. We like to be efficient. So, can we notice a way to count these things, right? Well, let's think about our moves as like a set, right? So the first time here, let's do this in yellow because it's what I drew in the first time. The first time, what moves did I make, right? I went right, right, up, right, right, and then up, up, up. Okay, cool. Now, okay, now the second time, right? Let's do this in green. What moves did I make? I went up, then I went right, then I went up, 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 and then I had to go right, right, right. All right, now here's the mind-blowing moment. Here's where I tell you how to count all this. So notice, to get from beginning to end, you can only make 8 moves in total, right? Because if you go right 4 times, that's it. You've already hit the right wall. Now you need to go up 4 times, right? If you've gone up 4 times, then the rest of your moves need to be going to the right. That makes sense. I don't think I need to convince you of that. I mean, like, just look at it, right? So we know all sets of paths from the beginning to the end will be of size 8. Okay, cool. Cool. Sets of size 8. Well, when we were doing binomial coefficients, we were dealing with sets of size 8. Now, but still, we don't really know how to count like all the differences in these paths of size 8, right? This is a more tricky counting problem, right? Well, notice, like I said, um, if you go to the right, you can only go to the right 4 times before your moves are forced, right? And if you go up, you can only move up 4 times before your moves are forced, right? So now let's not think of this problem as how many paths from start to finish. Instead, let's think about in how many places can I put an R, right? Let's just think about it like that, right? We only need to think about one or the other. Like without loss of generality, let's look at R. It could be U, because they're just arbitrary letters, they mean nothing. But for right now, let's just say R, right? This problem is becoming, okay, I have 4 R's I can use. I just want to know in how many different places can I put what's it called? Can I put these where can I place these R's, right? So I have 8 spaces in total. I have 8 spaces in total, and for 4 of them, I want to choose the letter R, right? I said that in a very specific way, so your brain can go off and start thinking, oh, I'll just use a binomial coefficient. The answer to this will be 8, choose 4. I'm not going to actually evaluate that. That's 8 factorial. That's an 8. That's 8 factorial over 4 factorial over 4 factorial, because 8 minus 4 is 4. I'm not going to evaluate that. It's perfectly fine to just leave it in this form because it's 8 choose 4 is way more specific than just some big number. But think about it, right? That's what we're doing. We have this list of positions essentially. We have 8 positions, and I just want to know how many ways can I choose 4 of those positions to be a right movement, right? Because then the rest will just fill with ups. And again, right and up are arbitrary. I could have said how many ways can I put 4 ups? Because then the rest will just fill in with R's, right? So that's a way to think about this problem. Not how many paths from start to finish by only going right or up. No, instead say, I have 8 moves. How many ways can I choose 4 of those moves to be a right move or an up move, right? I hope that makes some sense. If you don't believe me, you could do a smaller case, right? You could have a grid of a 3 by 3. I'll do that right now. You can have a 3 by 3 grid, because I'm not proving this. And then let's say that's not 3 by 3. And then let's say you have your start to finish. Here, let's draw the colors. Start and finish. And then I think this is it's still pretty big. This is a smaller case, so maybe you can go through all possibilities, but you'll notice with this, it's the same thing. You're gonna have a set. Sorry, that's a very big pen. You're gonna have a set of size 4 because you can only go right twice and you can only go up twice. And you're just gonna you're gonna ask yourself, okay, well, in how many ways can I fill in 2 spots to be a right position, right? Maybe like that, or like that, or like that, right? There's so many different ways to do it. And so your answer for this is going to be 4, choose 2, and then you can evaluate that number, and maybe if you want, count it all yourself to see, because you don't believe me. But I promise you, I'm not tricking you, that would be the simple way of doing this. You just take total amount of moves you can make, 8, and then half of those moves have to be going to the right, so you just do half of 8, right? So in this case, 4. 8 choose 4. Now, this would actually work a little differently. In some smaller cases, like I don't know if we had an odd amount of number. No. Actually, no. Ignore me. But yeah, this is how it would work. 8 choose 4. So now we're gonna look at another problem, right? So we're gonna do a little some analogy. I'll keep this on screen actually. An analogy about swimming, right? Let's say you're a swimmer, right? And you really want to go to districts this year, right? Well, how do you get to districts? Okay, well, you want to only go for your specific event, and there are 100 people in the conference that swim the same event as you. Now, the district's qualifying official people, they don't care about anything but the 16 fastest people. We have an 8-lane pool. We want 2 heats for our event, so we want 16 people to show up. That's it, right? So there's 100 people in total, and they would like to choose 16 different people. And my question is, how many different combinations of 100 people will make it to districts, right? How many different combinations exist? Well, like I said, we have 100 people in total, okay? We have a set of size 100, and the officials at districts are going to choose the 16 fastest. Notice how I keep using the word choose to express like how we can manipulate these like word problems into something we understand and then use the mathematical objects we understand. We have 100 people and we'll choose 16 of them. These are the total amount. This number right here. That's it. Those are the total amount of combinations of people who can make it to districts for your event. And now, as you could see, binomial coefficients really speed up these like counting problems, right? But then we can also throw this into probability. Say everybody has an equal chance of qualifying. Like say you're all just as good. Like you all have the exact same PR for some reason. And so now districts is like, oh, okay, well, we can't think of a better way to do this, so we'll just randomly pick 16 of you. You can calculate your odds of getting in, right? Say, so 100 to 16 are the total amount of people that can make it, right? So we would set up a fraction, right, where 100 choose 16 is our. I'm sorry, I have no idea why all of this is like moving all of a sudden. Where 100 choose 16 is our denominator, right? So we'll say 100 choose 16. And then you just have to count all the events that all the possible ways that you're in it. We'll call that n. And then that would be your odds of getting in, n divided by 100 choose 16. So as you can see, this isn't just some like stupid thing to count subsets of sets. These have actual applications in real life for counting and for probability and for much, much more. So if you found any of that interesting, thank you for making it to the end of this video. I hope you enjoyed it, and as usual, I hope you learned something.